Imagine trying to find one specific battery in a room where every item you own has been dumped onto the floor in a massive pile. Without a system, the search is a waste of time. Compare that to a supermarket. If you need batteries, you don't search the whole store. You go to the electronics aisle, find the correct shelf, and grab exactly what you need in seconds. For decades, chemistry was stuck in that messy room. Scientists had identified dozens of elements, but they lacked a logical system to organize them, which made it difficult to predict how these substances would interact. We are going to build your mental supermarket. By the end of this video, you will be able to memorize key element groups and calculate the group, period, and valency of any element using only its atomic number. Early chemists, notably Dmitri Mendeleev, attempted to organize the elements using their atomic mass. They arranged them by how heavy they were. This chart shows the early Russian grid. Because it relied on mass, the arrangement occasionally forced elements into columns where they didn't belong, breaking the pattern of predictable chemical properties. The solution arrived with Henry Moseley. He proved the identity of an element is determined not by weight, but by its exact proton count. Moseley established the modern periodic law. He removed mass from the equation and arranged the elements sequentially by their atomic number. Every element from 1 to 118 was placed in a specific mathematical order. The atomic number provides the foundation for every modern chemistry calculation. Think of the modern periodic table as a map of specific addresses. To find any location, you need to understand its two axes. First, we have the vertical columns. There are 18 of these pillars running from top to bottom, and we call them groups. Next, look at the horizontal rows. There are exactly 7 of these rows running left to right across the board, known as periods. Once you know an element's precise group and period, you have isolated its exact, unique coordinate on the grid. Memorizing 118 individual addresses through repetition is slow. Instead, we use specific mnemonic patterns to lock in entire vertical groups at once. For group 1, we use the Hindi phrase, Hali na ki rab se faryad. That sentence gives you the exact order: hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. For group 2, the pattern is just as fast. Deta mange kar skuter babrazi. Beryllium, magnesium, calcium, strontium, barium, and radium. Linking these elements to familiar phrases turns hours of rote memorization into a 5-second recall. You can find an element's position without looking at the table. You calculate it by taking the atomic number and mapping its electronic configuration across the K, L, M, and N electron shells. Take sodium, element 11. Its electrons fill the shells, 2 in K, 8 in L, 1 in M. Rule 1. Total shells dictate the period. 3 shells means period 3. Rule 2. The outermost shell defines the group. 1 valence electron equals group 1. Watch out for this rule. Chlorine, atomic number 17. Its configuration is 2, 8, 7. 3 shells means period 3. Its outer shell has 7 valence electrons. If it's more than 2, add 10. 7 plus 10 is 17. Chlorine is in group 17. Electronic configuration provides everything you need. By identifying the shells and applying the +10 rule, you locate any element on the grid. Let's review. Elements are sorted by atomic number. The table has 18 groups and 7 periods. Map your electron shells and add 10 if the outer shell holds more than 2 electrons. Now that you have the tools, it is time to apply them. Grab a piece of paper. Question 1. What is the period and group for calcium? Question 2. What is the valency of oxygen? Question 3. Which element is located at period 2, group 14? Put your answers down in the comments. You now have the ability to read and navigate the most complex chart in science. Post your results, and I will see you in the next lesson.